Hi Year 13s, this is just a quick video to go through some of the notes from today's lesson. So hopefully you've had a go at the starter. I'll make sure the answers to that are on OneNote. There's a little reminder about the investigation from last lesson, a little reminder of the findings. I guess we should put this in a green box because this is something that is worth remembering. So let's put the whole thing in a green box. So this is a result that you should learn for this topic. Okay, so we're going to move on to something called a transition matrix. I think we've talked about transition matrices when we did the Markov chains. We're going to link it to graph theory today. So we're going to talk about a random walk. A random walk on a graph is a walk in which the vertex moved to is chosen randomly from those available. So if you get to vertex A and there's three options for three edges that leave A, we're just going to assume that it is chosen at random. So each of those would have a probability of 1/3. And what we can do with this is we can create a transition matrix for all the places that we could go. And if there's a finite number of vertices, which for the situations we're looking at there will be, a random walk will become a Markov chain. So we can use that maths that we looked at before, I think in the matrices unit here as well. We can do this for directed graphs, which obviously need a little bit more care taken of them, and undirected graphs. And the probabilities give us a bit of an idea of what proportion of the time we're going to spend at each vertex if we ignore the transition time and if we assume that it is completely random and every choice is independent of the ones before. The one key thing that is tricky here, well, it's not tricky, it's just something we have to remember, is that the direction of movement is different to that of an adjacency matrix. So we were looking at adjacency matrices last lesson and we know that they went from and to. That was how our adjacency matrix worked. I think that's how we spell adjacency. Adjacency matrix. Right, the transition matrix works the other way round, which is tricky to remember. Transition matrix goes the other way round, so we're going from to. All right, and so what that means is, so let's say this first column is all the places leaving A. All of our probabilities will go in this column. So going to A, going to B, going to C, and so on. And we should find that adds up to 1. And that makes sense, right? Because if we're at A and we've got to make one of those choices, when we add up the probabilities, it's got to sum to 1. It certainly will go somewhere. Okay, so that's something that we're going to have to be a little bit careful of. All right, so we can make a transition matrix, and then of course we can use the ideas of Markov chains to find what happens after a certain number of steps through the changing of the states. We could do high power and find the steady state, which gives us kind of the longer term proportions where we'd be at each of the vertices. There are some examples that you should, there's only 2 examples actually that we should have a go at the bottom of page 12. Before that, we're going to talk about the Google PageRank algorithm because this links to it as well. So it's a nice little example of something that we come across probably every day, unless we exclusively use ChatGPT. But yeah, it's something that was developed in 1996. And the idea is that we want to be able to rank web pages in terms of how likely they are to be useful, so that the most useful web pages are at the top of the search results before the least useful ones. And what it does is this algorithm, it looks at the links from web pages as edges in a directed graph. So we're thinking about an important website has been defined as one where other websites link to it, as opposed to an important website being one with thousands of links on. The links leaving the website are not showing its importance. It's the links that take you to a website that make that website seem more important. So we'll look at a really simple example of it here. Here we've got A, B, C, D, E, F. We've got 6 different web pages. The edges indicate links between the pages, and they're all directed. Taking a very quick look at this, maybe our assumption would be that website D looks like the most important because it's got the most links, or maybe website A. Then we have to think, oh yeah, it's the edges that go into the vertex that are the most important. So let's look at how we can create a transition matrix, and then how we can use that to decide what is the rank of the vertices. So let's start with our transition matrix. I'm going to call it, let's call it T for now. Okay, and I have to remember to go from up here. So A, B, C, D, E, and F. And I'm going to go to these websites. Okay, hopefully I've left enough space here. All right, so I'm going from A. So let's just look at website A to begin with. Where can we go from website A? Well, there is one edge that goes to F, and there's one edge that goes to B. Oh, and one edge that goes to D. Okay, so there are 3 edges leaving A. So if I'm on this web page A and I'm going to take one of the links, it's going to take me to B, D, or F. And if I'm choosing those randomly, they will each have a probability of 1/3, and there is 0 probability that I can go to any of the others. Okay, so same idea, we'll do one more of these together quickly. So B, here's website B, webpage B, it only goes to D actually. It's got 3 links going to it, but only 1 coming out. So if we're on website B and we choose a link at random, it is certain I'm going to go to D. And I can fill all of the rest of these in as 0s. All right, so you can work your way through and fill out the rest of the transition matrix. If you want to pause the video, do that. In part B, it says find the steady state probabilities for the network. Well, we know steady state probabilities, that's kind of our long term. So the technique that was the quickest, most efficient way of doing this was to take matrix T, put it to a very large power. What we're going to notice in this unit is the matrices are going to be much bigger than what we were dealing with before. It's very common for them to be 6x6 matrices like this, or even slightly bigger. You do need to take care. It is time consuming filling them out, but the marks awarded do allow for that, but do try and take care with it. I feel like they're not really going to get any bigger than 8x8 in your exams, just because it's going to take time to fill it out. But yeah, make sure you've checked everything over, because we all know that it's very easy to have one small mistake and not really notice it. Unless it's a really big error, we might not notice it. So for part B, we're going to raise this matrix once we've finished it to a very large power. We'll be able to see the steady state probabilities, and we'll be able to rank the vertices based on who has the biggest probability. Biggest probability is the website that is the most likely to end up at, and therefore it suggests it's the most important. Okay, so finish this off, have a go at the other examples, and I will see you next lesson. Bye-bye.